so important. And we have this guaranteed bandwidth which makes it real-time capable. Yes.
Or is it like token ring?
Yeah, it's a shift register. It's not like token ring. It's like, yeah, you put from one entity to the next entity, and it copies it to the next, and so on.
Maybe 32 bits for every entity, and then you have to shift it through the full whole thing?
Yes, yes. These 96 bits. So you have to shift it in one cycle from one entity to another. And that's a very nice feature, I think. So the FlexIO, it's just to communicate with the outer world. It's also because if you're a computer scientist in supercomputing, one processor is not cool. You need at least 1,000, and therefore you need a FlexIO to interconnect the processors, for example, directly or indirectly with the network. We have very fast connection, so it's just 60 and 96 pairs in the whole is just important, as you see how many pins the processor must have, at least several for the voltage, and at least these 96 pairs to communicate with the mainboard. We have 7 lanes with 44.8 gigabyte per second outgoing, and 5 lanes with 32 gigabyte per second incoming. So it's a real cool network, I think. And also very nice is that we can connect 2 processors glueless. So while designing the cell, they just were designing a dual cell in the same thinking. So just you put two cells together and you have a dual processor with no cost. You just can add them. It's a little bit like the Opteron here I've written. It's comparable to HyperTransport. You have coherent and non-coherent links. Basically, of coherent links, you can build a CC-NUMA architecture, and it's going to be more and more interesting. There's the first dual cell blade available from Mercury Systems, which just put 2 cells together without a switch, because they can connect it gluelessly. And you can just put 4 or 8 or more, and you just need a switch on the system. That's like a normal network, I think. It's not published much, but I think it's like a normal network. So then we have a memory interface controller just to access some more memory than our 256 kilobyte. That's connected, of course, to XDR. Also, just look at the number here. I don't have to say anything else. It's 25 gigabyte per second. And funny thing is, why is ECC protected? So it's designed in the cell documents as ECC protected memory. Maybe IBM is going to use it as a server, because I think ECC, everybody knows ECC is not very important for PlayStation, or maybe HDTV, where 1 pixel will shift if some radiation comes. But for a server, it's very important. And yes, I'm not sure, but maybe somebody can tell me at the end of the talk. So they have a conventional protection system, I already told you. They use virtual addresses, and they have no cache. So the memory is not cached. Only the PPE is a cache, and the rest of the system is uncached. What is going to be different in the programming of the cell? So we are not programming at an abstract model like the x86. In the x86, we are programming an abstract language, so like it was designed decades ago to support some very old processors, and everybody just keeps it up, keeps it alive due to compatibility reasons, just not to lose any customers. And it's going to be difficult, of course. I'll show you. And we have the same problems as multicore, because we have to parallelize. We have to think about this, how to parallelize our code, not the compilers doing it, not implicit instruction parallelism. It's just we have to think about everything. And assembly is available, of course. We are programming it directly. We can program in C. I already told this. We can virtualize the SPEs in the operating system. That's also very interesting. So the the operating system is allocating the SPEs for a specific task. A Linux version is already available, which is doing this. It's very nice. And PPE code is usually PowerPC compliant, and Linux was running without any modifications, but it wasn't able to use the SPEs, of course. So there were modifications done to the Linux kernel to use the SPEs, and I think IBM is trying to push it into the mainline kernel, so I think they're quite successful. The SPE code must be self-contained. It's also very, very interesting. So that's like a small, the SPE code is basically a small program which is runnable without anything else. So you just can put it on this small SPE and it runs, and yeah, it processes. And an auto-vectorizing compiler is available from IBM called Octopiler, but I don't think that it's going that good because I didn't try it, to be honest. But I think there's no auto-vectorizing compiler yet which is working better than a human optimizing some code. So basically, all these PlayStations and PlayStation games are, in my opinion, programmed by hand and optimized by hand and written mainly in assembler. So I hope you're also going to do this. So I'm giving this talk that you're going to develop cell programs, you're going to port John to Cell, or maybe other very interesting programs with these programming models, of course. So it's just what you can think of. Job queue to enqueue multiple jobs. You can build a self-multitasking SPE, but I don't know if this is going to be very useful. But you can make stream processing, of course. Stream processing is very, very important for managing these decoding video streams and displaying HDTV and playing video games and all this stuff. Okay, for video games it's not that important because you need to react very fast. You can implement a software-managed cache. It's also very interesting. And maybe MPI. But that's more personal thing for me, MPI. I discussed a long time with the IBM guys which prefer the shared memory model, but we'll see. So, summary and conclusion. What can we do with the cell processor? Why am I here? I'm just here to tell you about the new processor generation which is going to come, and to encourage you to look at the cell, look at the simulator, and see the power which is behind it. So program your applications like very, very cool demo applications or something, which are going to be run very fast on the cell processor, or yeah, something else. The PlayStation 3 is coming out, or maybe not. We'll see. It should come out this spring, but I think it's very, very short for Sony, and it's very tough for Sony to get it working until spring. And they told that it's going to be only at 3.2 gigahertz. That's not very nice. And it's going even worse, because they say we have only 7 SPEs to the programmers which are programming the video games. And that's very interesting, because nobody knows why. The first idea was, okay, they're trying to increase the production yield. So they're just switching off broken SPEs like Intel or AMD does and sells them like a cheaper one. But then some deliberations came up that, okay, the production yields are going to be very, very high because the production started yet. I think it's the cell processors in production, and the ramp-up phase, how it's called for a microprocessing company, is going to be finished soon. And yeah, then the yield, they could just enable all 8 SPEs, but maybe they're using an SPE for a dedicated rootkit or something. I'm not sure, because it's Sony. It's Sony. Sony is selling the PlayStation, Sony is programming the PlayStation, and Sony is programming the operating system for the PlayStation. This Ken Kutaragi told us that we are going to expect a Linux version, like for the PlayStation 2. So I'm very, very interested in this version, and I would be very happy to see this. But if it doesn't come, then I hope we can manage it to put a Linux on this box. So the second application is server applications. So IBM, basically a good friend maybe, Mercury, thinks that these cell processors is very, very, very mighty, and it's very good on server applications, on servers in general. So they sell yeah, a blade server, which is compatible to the usual IBM Blade Center with 2 cell processors. Fortunately, they have 8 SPEs enabled, so another evidence for the rootkit. And it's running Linux, of course. And yeah, more applications, just find it. So how much time do I have left? Oh, fuck. Okay, sorry. Yeah, I just skip it. Very interesting is that we could beat the world's fastest supercomputer with 131,000 processors with just 14,000 cell processors with dual precision. With single precision, we would just need 1,400. So you see, but unfortunately, this top 500 list, which is ranking these processors, is dual precision. So they just give the problem for dual precision. But you see this, and it's really going to be a very cheap. I've heard about $100 something. I'm not sure. A very cheap processor, which is extremely fast. So you have 256 gigaflop versus 4 on today's current processors. Okay, and so on. And now I'm going to show you the practical, more or less practical demonstration. So I hope it's going to work because, oops, oh, I have a mouse. Basically, IBM is providing a cell simulator. I'm going to start it right now. It's a real cool thing because it simulates the whole cell processor with all SPEs and it runs Linux. And it runs under Linux, I think only. So this is basically the console of the cell processor. This is the cell processor itself. I think I can raise the font a little bit. Oh God. Yeah, this arrow is coming every time. So we see, just ignore it. We see these 2 PPEs. So it's a dual cell, or it's a cell with at least 2 PPEs and 7 SPEs. I don't know where the other 8. Sorry, I don't know where the other 8 SPEs are gone, but yes. Basically, it works in the following. You can just, oh fuck, my start button is gone. So there should be a start button, but I think I should go down again with a sorry for this. So now we have a fast mode. That's very interesting. So the fast mode enables or disables everything which is related to tracing the code. So timing, information, and all this stuff. And it's really going 10 times faster than the normal thing, the normal simulation. So. And you have to see, it's on my very, very slow notebook. It's only a Pentium system. And it's booting up Linux on the cell. This is the cell console output, and it's booting up a Fedora core, yeah. But, and another interesting thing is that they, on the web page, they say that, okay, it's just install it under Fedora core. But this is Gen 2, my notebook, because I don't like Fedora. You can just copy all the libs from the Fedora system to the any system else which is running a Linux kernel, and it works. So this is basically our cell. And the first thing I'm going to do on cool systems is this. Oh, sorry. Yeah, we see broadband engine. Oh, 2 gigahertz, cool. That's a very fast thing I have here. And yes, so that's the IBM codename. IBM basically calls the cell processor cell broadband engine, so CBE. And yeah, running with 2 of them on the simulator. And now I think I'm going very short. I have a small test program, which I will just compile. Okay, is this compiled? And I'll describe it later because it takes very long to simulate. And there's also a very nice feature to interoperate